quantum computer operates on a quantum state rather than a classical one. One reason this is interesting is because of the possibility of using all this additional richness of these entangled states. The state of a classical machine with n objects that can each be in one of two different states can be described by n binary digits. By contrast, a machine dealing with n two-level quantum mechanical systems could be performing an operation on 2 to the power n numbers at once. No classical machine can do that, even for moderate n. As we said, for n equal to 300 quantum mechanical objects, each with two states, we need 2 to the power 300 objects to store the information for the quantum mechanical state. And there simply are not enough atoms to store 2 to the power 300 numbers at one atom per number. It's well known in computer science that many problems have the unfortunate property that the required complexity grows very fast as the scale or the size of the problem increases. No classical computer could possibly solve such problems once they get above a certain size. Perhaps a quantum computer, working with quantum mechanical systems of some moderate size, could solve such problems. Quantum computer algorithms have been developed for at least two important problems of this type. The first such quantum algorithm to be proposed was for finding factors of large numbers, a notoriously hard computational problem. This problem is so hard that we routinely use that hardness in constructing the encryption algorithms we use every day to send secure information. The algorithm that would run on a quantum computer to factorize large numbers is called the Shor algorithm, after its inventor, Peter Shor. The second such quantum algorithm could be used for searching databases, a problem essentially like trying to look up a telephone directory backwards. Given the telephone number, can we figure out whose number it is? This is known as the Grover algorithm, after its inventor, Lov Grover. A quantum computer is, however, not necessarily an easy thing to make. One thing we should understand is that it would work in a very different way compared to any classical digital computer. A classical computer takes data as bits, processes it in some kind of black box, and gives an output as bits. A quantum computer, however, would not work with bits in the conventional sense. Instead of bits that are only 0 or 1, it would work with what are called qubits. Qubit is spelled Q-U-B-I-T. Qubits are represented as the linear superposition of two states of a quantum mechanical object. The object might be an electron spin in a linear superposition of spin up and spin down. Or it might be a photon in a linear superposition of two different polarization states. Or it might be an atom in a linear superposition of two possible states, a lower or ground state and an upper or excited state. So we could write a qubit state in the following form. We could call the state psi, if we like, and write it like this. And here, 0 would be the quantum mechanical state that is representing 0, or logic 0, if you like. For example, it could be a horizontal polarization state H of a photon, or perhaps it could be a spin-down state of an electron, or possibly a ground state, G, for example, of an atom. And similarly, in this expression, 1 could be the quantum mechanical state representing our logic 1, if you like, and could be physically represented by, for example, a vertical polarization, or spin up, or an excited atomic state, maybe E. Because of normalization, these two coefficients have to be such that the sum of their modulus squareds adds up to 1.